Hi, I'm Steve Ward. I'm a pre-sales consultant at Emerson, and in this slide deck I'm going to run through the steps that you need to perform in order to create a bill of materials for one of our PACSystems PLCs, and we'll also be covering how the I/O is configured as well. First of all, a safety moment. Emerson is very concerned with safety, both at a corporate level and for our employees and our customers and clients. So the important thing is to stay safe. Review your working environment for issues and look for any hazards, and if there are any possibilities of incidents, then you're encouraged to stop work and then make sure that any unsafe items can be rectified. Issues should be reported, including near misses, because near misses, although they might not be a safety incident, it could be something that next time, if we can prevent, then we make environments safer. And pay attention to these 12 life savings behaviours. So let's move on to the bill of materials creation process. So our standard go-to-market strategy is to supply PLCs and related products as components. And then what happens is an end user or application requirement is used, and this allows us to define certain components and then allow those components to be assembled into a system. For many projects, our pre-sale scope is to provide a hardware list in the form of a bill of materials, or BoM, sometimes known as a bill of quotation or BOQ. Now, the reason for having this bill of materials is that then sales and customer care can turn that bill of materials into a quotation, including prices and delivery times. Now, ultimately, as per Emerson terms and conditions, the client is responsible for ensuring that the quoted items meet the requirements of their application, but the pre-sales role is very important in order to be able to confirm those requirements initially into a suitable set of parts. And that's a vital part of the pre-sales scope. Now, there are many questions that need to be answered in order to make the bill of material, but they come down to a few simple questions, but there are lots of options that might also need to be addressed. But at the basic level, the first thing we need to know is how many I/O and what type. So for example, discrete in, discrete out, or digital in, digital out, analog in, analog out, any RTDs or thermocouples, any high-speed counters or pulse inputs, any HART I/O. We might need to know what is the power supply, either is it DC or AC. Maybe is an energy pack required in order to store values across a power fail for non-retentive storage. In many applications we can make assumptions if it's a small application that it will be local, but maybe there will be remote I/O, so we need to know how many drops. Is the system redundant? Maybe to help the CPU choice, we need to know what type of application it is. Depending on the simplicity or the complexity of the application, we might choose a smaller or bigger CPU. Are there any communications to other devices? And if so, what protocols? Serial, Ethernet, what protocol type? Are we the master or the slave? Are there any special application requirements? Is there a specific temperature rating? Many factories are 0 to 60, but if you go to the Middle East or offshore, you might be looking at -40 to +70. Do we need ATEX, for example, for explosive atmospheres, or IECEX? And in some cases, that ATEX designation or the temperature designation might also need conformal coating. And are there any other special requirements as well? In a modernization project, we need to know what is currently installed, and then we can also offer options for adjacent products. For example, spares, maybe there are Ethernet network switches, variable frequency drives, industrial PCs, and we can also offer software and services. If the questions can't be answered, we can make assumptions for a budget quotation, but we need an I/O count as a minimum. Typically, for a modern system, I would assume digital in, digital out is 24 volt DC, and I would assume that analog in and analog is all 4 to 20 milliamp. And unless specified, I would assume there's no temperature inputs, no high-speed counters, and that HART I/O isn't required. For the power supply, I would assume 24 volt DC, And under the low voltage and machinery directive, 24 volt DC is a good practice anyway, because you want to have a safe panel, and if you've got high voltages, then that reduces the safety. For the energy pack, I would assume yes. Some of our CPUs already have a built-in energy pack, but for some it's an option. So assume yes to begin with, and it can always be removed if there's some optimization required later. For a simple application, we assume local I/O, and we would also assume simplex controllers, but there's always the possibility to offer an option for redundancy. So we could have two quotations, one for simplex and one for redundant. But again, maybe we need to know what the type of application is, because that can help us make the CPU choice, but also for many applications we can decide if we need simplex or if we need redundancy. If communications aren't specified, we can assume using the standard built-in Ethernet port is adequate. And for environmental requirements, 0 to 60 is straightforward. And for many of Emerson's PLCs and I/O products, we're automatically ATEX Zone 2, so that's quite straightforward. Another assumption would be safety. Safety needs special consideration, so we would assume that for most applications, everything is standard PLC and it's non-safety, so there's no SIL, there's no performance level. Instead, everything is in a safety type of environment. Notice safety is different from the ATEX requirement, so you get both safe and non-safe atmospheres, so that's where ATEX would come in. But under IEC 61508 and ISO 13849, you also get machine safety and process safety. So I'm referring specifically to the 13849 and 61508 standards here. So for machine safety under EN ISO 13849, we have the option of using the PACSystems RSTi-EP safe feed inputs. And for process safety under IEC 61508, we can either quote our PACSystems Safety Net, which meets SIL 2, or we could refer clients to our Delta V colleagues who can provide the Delta V SIS, which is SIL 3. Now, safety is not going to be covered in this deck. It is quite a specialized subject, and ideally you would need to have a lot more knowledge and experience of safety systems before you apply it. But it could be that if there is enough information from the client, it's certainly quite easy to quote the RSTi safe feed inputs. It's a bit more difficult when we come on to the PACSystems Safety Net side. So I'm not going to talk about safety in this deck. We can cover that in a separate deck. So here are some examples of worked creations for bill of materials. Now, the way I like to create a bill of material is subdivide the application into the controllers, the I/O, then add the programming software and extras, and if it's modernization, that needs a slightly different approach because you want to look at what's installed and then quote for suitable replacements. So for controllers, we can start off with a simplex PACSystems RSTi-EP CPE 200, and that's ideal for compact applications. This would typically use local I/O, but we have got the possibility of PROFINET remote I/O as well. For more high performance applications, we could move up to the PACSystems RX3i, which is rack or chassis based, and again with local I/O. For redundancy, we can quote either the PACSystems RX3i rack based application for high availability applications with high performance with single scan failover, or we could quote the edge controller. And the edge controller, that has multiple uses. It can be used for larger distributed applications and also for high availability applications which need a failover time of 300 milliseconds. Now with these applications, local I/O is straightforward. With remote I/O, that's often used for distributed and high availability applications, so that would be a separate part of the quotation exercise by doing that remote I/O separately. So for remote I/O, we've got a couple of options. PACSystems RSTi-EP PROFINET remote I/O, or we could quote the RX3i PROFINET remote I/O, and there are other options such as Versamax and PAC 8000, but I'm going to stick with RSTi-EP and RX3i in this deck. So extras could include an operator interface such as our Quick Panel Plus or upcoming PACSystems operator interface. It might include power supplies to convert from mains down to 24 volt DC. It might include network switches, And of course there would be the software on top of that. And I've got a separate slide deck which covers our Movicon HMI SCADA and how to create a bill of materials for the Movicon software. So here are some slides which show how that architecture might work, and that relates the previous slide into the sorts of solutions we have. So micro PLC, that would be performed using our upcoming PACSystems micro PLC, or possibly using an operator interface talking directly to remote I/O. So with the operator interface, the Quick Panel Plus and the PACSystems operator interface, they include an IEC 61131 Part 3 programming engine which can control I/O using either Modbus TCP or using Ethernet global data. So Modbus TCP would allow you to quote an operator interface with RSTi-EP I/O, and then you could also quote EGD using perhaps Versamax I/O or even PACSystems RSTi I/O, but by that time you're probably increasing the price of the system and the panel space, so RSTi-EP would be the way to go on that one. With the upcoming PACSystems Micro PLC, that will give you the option for a standalone controller with embedded I/O, and that also includes PROFINET support, so you could extend to PROFINET remote I/O including VFD capability. And in this case, because the Micro PLC is the controller, an operator interface might be an optional extra for user visualization. Micro applications are typically up to about the 200 I/O range, and then there's an overlap there with the next set of slides or blocks along, which is the compact systems. So with compact system, we have the PACSystems RSTi-EP, and this time it's a CPU which is more powerful than the micro or the operator interface engine, and it allows for more I/O modules, including more remote I/O options, including PACMotion VFD or even remote I/O. Now generally with the compact solutions, they're in the range of 100 to 500 I/O, and the operator interface is optional. And also you could have optional HMI SCADA above these, but as I said, that's a separate slide deck. Now for larger applications, where we need larger amounts of I/O or higher performance, or where we need motion control, then currently this is where our PACSystems RSTi would come in. So again, PACSystems RSTi with optional operator interface, and then we have a variety of local I/O and remote I/O options. For remote I/O it would be PROFINET, again giving us the possibility of integrating PACMotion. We could also use RSTi-EP I/O, and there's other I/O options as well. And for the motion side, you would use a motion control module with EtherCAT interface to our PACMotion servo modules. So typically with these larger PLCs, they're 250 I/O upwards, and that could include your distributed I/O count as well as the local I/O count. Now for high availability, we have two redundant PACSystems CPUs, and they're synchronized using reflective memory, again with an optional operator interface. And then typically with these redundant systems, we're using a fault-tolerant PROFINET ring. All the devices have built-in switches, so we don't need external switches, but the idea of adding a single extra network cable from the first device back to the last device, that gives us additional fault tolerance using the media redundancy protocol. So for these high availability systems, it could be RSTi-EP I/O. Maybe you need heart integration, which is where RSTi I/O would come in. And maybe it's a process control application, so maybe this is where you might consider PAC 8000 I/O. And the last one on the right, we have edge capability. So this would be a simplex or redundant edge controller application using our CPE 400 and CPL 410. Again, optional operator interface. Because it's a edge controller, there's quite likely integration up into the cloud. And then we have a variety of different sorts of I/O, typically for RSTi-EP, but again, other types of I/O are also supported, depending on what sort of control you have and how much I/O there is. So we don't have a recommended I/O count for edge controls. I've seen some very small systems using an edge controller, but it can also do some very large systems, and the same with the high availability side. I would say that typically if it's a smaller high availability system, an edge controller redundant would make sense, but for larger applications, the PACSystems RSTi using reflective memory makes more sense. And then above this, of course, we have PACMachine Edition. PACMachine Edition is our programming software, and then you may also have the Movicon HMI SCADA. As I say, that's on a separate slide deck. So just to confirm that, these are our preferred approaches based on the I/O count and the application complexity. So simple systems use a micro PLC. That will be available in 2026. Ideal for small, simple applications up to 200 I/O, generally all with the I/O in the same place, but it will support remote I/O with PROFINET, and maybe with small, simple motion, either using hardwired with high-speed counters and pulse width modulation type outputs, or using maybe an analog output. There's also some possibility there for VFD integration via PROFINET, but generally for small, simple applications. For larger applications, we have the RSTi-EP CPE 200 with local I/O. More powerful CPUs, again, ideal for small, simple applications, and certainly what we would offer today. In future, as the micro PLC becomes available, it will still be suitable for smaller to medium applications where maybe there's a bit more complexity, maybe you need a bit more memory, maybe a bit more communications, maybe you need some sort of remote I/O capability, and certainly for slightly larger applications. The PACSystems Edge controller with RSTi-EP I/O, ideal for any application requiring an integrated PAC edge. Also suitable for medium and large to complex applications from about 250 I/O upwards. And again, for redundancy, we support that failover time of 300 milliseconds, so a good option for redundancy applications. For large applications, this is where PACSystems RSTi rack-based comes in with either local I/O, remote I/O, and also for any application requiring PAC motion servo, that needs the PMM345 module in the RSTi, so that would have to use the RSTi as we are today. Ideal for medium to large and complex applications requiring high speed, again 250 I/O plus. For redundancy, ideal for applications which need very high speed redundancy with single scan failover times in the order of 5 to 20 milliseconds. Very good for Series 90 modernization. And also for applications requiring Heart I/O and pass-through, you use the PACSystems RSTi Heart I/O, which then gives you that integration. You could use that with smaller CPUs, but you would still be needing the RSTi I/O modules. There is now an RSTi-EP Heart module as well, but it's a bit more limited compared to the RSTi Heart I/O, which gives you full through pass-through to applications like AMS, which is Emerson's asset management system. Now, while we're talking about Heart and integration with AMS, we also offer MTP support. MTP, which is the media type package or module type package, this would really work with any of these solutions, but probably it's going to be used on skids and similar applications. So you could use it on the CPE 200 or an edge controller or an RSTi. The difference is that you have to use the MTP function blocks, so they're maybe going to use a bit more memory. And you would also have to think about using the correct programming software. You'd need PAC Machine Edition Pro Plus software, which is the one that's required for integrating the MTP function blocks and doing the XML export into the DCS system. So the PACSystems Micro PLC is still to come. So I'm going to start today with what we have available for 2025, which is the PACSystems RSTi-EP CPE 200. So again, compact solutions, simplex solutions, maybe in the order of between 100 and up to maybe 500 I/O, and also simple applications, although we do have a range of CPUs here with different sizes and different capabilities. So I'm going to divide this up into steps, and the steps are quite straightforward. Step 1, add a CPU. And we only have 5 CPUs in this range. 5 CPUs covers, I believe, the majority of applications. We've got the entry-level CPE 205 with 0.5 MB of RAM, which gives you more than enough for quite a large application, but depending on the complexity of the application and the amount of I/O you have, and particularly for PROFINET devices, 0.5 MB might be a bit limiting. So I would say if you're not sure, you'd probably quote the CPE 210. That gives you 1 MB of RAM, which is much larger, and that would be suitable for a lot of different applications. If you need more RAM, or if you need DMP3, then we've got the CPE 215 with 1.5 MB of RAM, CPE 220 with 2 MB, and then the largest model is the CPE 240 with 4 MB of RAM. So with these, very straightforward quotation process. It's a single part number. You just quote that part number, and that includes everything you need, including the DIN rail mounting, the DIN rail clamps, the expansion capabilities, the memory capability. It's all included. There's no other parts required other than the actual CPU part itself. So here's what your bill of materials might look like. Quantity 1, part number EPX CPE 210, and of course your description. So from the datasheet, or from our Salesforce CRM, or from a predefined spreadsheet, you could very easily just select that line or copy that line or paste that line into your Excel spreadsheet you're using for quotations. Or maybe you're just pasting directly into an email. For simple quotations, I just email directly. For more complicated quotations, I like to create an Excel spreadsheet. And of course, you could also copy and paste into a Word document. And this can also be used as the basis for import into our Salesforce CRM if you've got a pre-existing bill of materials that you want to create a quotation for. But anyway, it's simple. Add a CPU, single part number. It's just a matter of deciding which part number to use. Now for a standalone compact system with local I/O, the next step is add the I/O modules. There's no backplane, there's no power supplies, there's no chassis involved. Each I/O module plugs directly to the right of the CPU, and then you add as many modules as are supported by that particular CPU. So example modules include the EP1218, which is a discrete input at 24 volts, and that supports 2-wire connection for up to 8 points. 2 wires is good because it means you don't need any other terminal points, but many users don't like wiring directly to the I/O. They prefer to wire to intervening I/O, so having that 2 wires isn't necessarily very helpful. So for many applications, we would start with the EP125F, which is the same discrete input, 24 volt DC, but now we have one wire for each termination, and then there would be a common which would be wired via your extra terminals. Now generally, the 1-wire modules are lower cost than the 2-wire modules. First of all, you only need one of them, and then it's also cheaper from the point of view of 1 versus 2 modules. Also allows you to have more modules in the chassis, but you do need the extra termination for the return wires, assuming that each of your devices has 2 wires. So for most applications, we quote the EP125F, and then unless it's a very small I/O count, that will give the user the sort of standard PLC type arrangement they're used to, with a set of terminals for the actual I/O wiring. Again, there are some possibilities here for reducing panel space and for reduced third-party component cost. That's where the 2-wire terminals come in. But for many users, we would start with the 1-wire terminations if we're not sure. Another possibility would be to give 2 options on the quotation, one for 1 wire and one for 2-wire. Now we've got the same on the output side. We've got the EP2218, which is a discrete output module, 24 volt DC with 2-wire, and that has 8 points. But there's also the preferred one, which is EP225F, and this is a discrete output, 24 volt DC, 1 wire now, so 1 termination per output, and 16 points. So it gives you higher density, but again you need those extra terminals for the return wire or the 0 volts. On the analog side, I would typically quote the EP3164, which is an analog input supporting voltage and current. This is a 16-bit module. We have got the option of going to a 3124, I think it is, which is the 12-bit module, but the 3164 is 16-bit, and that supports 4 points or 4 channels, and that gives you wiring for 2, 3, and 4 wire. So in this case, it's quite straightforward. We do have an EP3368, which is a high density module, but that requires additional components. So for simplicity of the offer, I would normally use the EP3164, which gives you 4 channels. And then on the output side, again, we've got a similar module, 4164, which is your analog output, again with 2, 3, and 4 wires and 4 points. So this makes your bill of materials very straightforward, as you can see on the right. You've got one CPU, you've got however many input modules you need to meet the input requirements, how many output modules you need to meet the output requirements, and then it's just a matter of using the correct number of modules to meet your I/O count. So for example, if you were requested for 128 inputs, you divide 128 by 16, so that means you would need 8 of the 16-point modules, because 8 times 16 is 128. There might need to be a calculation there for spares. Often I see specifications ask for an I/O count and then specify 20% spare on top. So you could multiply your 128 by 1.2 to get your 20% spares and then divide that by 16. Or you could do your divide by 16 calculation first and then multiply the 8 by your 1.2. So for 20% spares on 128 inputs, that would typically be 10 modules rather than the 8 that you really need. Now on the right hand side, this is possibly all you need, but we do have the options for output power feeds. And the reason for that is on the input side, we have a 10 amp independent supply for inputs, and then we have a separate 10 amp supply on the outputs. Now for inputs, 10 amps is probably more than enough for all of the inputs you would have in a chassis. But on the output side, if each of those discrete outputs is running at say half an amp, you're typically limited to 4 amps per module. So what you could do is you could do a calculation based on the output current plus the simultaneity factor, which is how many outputs are on at any one time. The reason we do that is with many systems, if you're controlling, for example, a pneumatic cylinder, there's one output for energize and extend, and there's another output for de-energize or retract. They're not on at the same time because that would be pointless. You can't retract and extend at the same time. You might even end up damaging the system. You'd certainly be wasting air, and the system probably wouldn't move, or maybe it would move very slowly in a random direction, depending whether the extend or the retract is more powerful. But there's your simultaneity factor. It's 50%. Only half the outputs are on at any one time. And it might be your solenoid isn't half an amp, maybe it's only 1/4 of an amp. But assuming 4 amps per module, you can see there that, depending on the number of points, you might say, okay, well, I'm going to have 128 outputs. You might say that my simultaneity factor is 50%. So that means that now I've got 64 outputs. You might say they're only running at 0.25 amps each. So that would bring you down to 32 amps. For 10 amps isn't enough. So what you would do is you would add some EP7641 power feed modules, which would give you an extra 10 amps. And if you had 32 amps, you would need 3 of those EP7641s in order to be able to control your 32 amps, because you'd have 40 amps in total, including the CPU. Now that sounds complicated, so there is a power calculation utility we have which you can use to calculate exactly how many of those power feed modules you need. So for more complex and larger applications, particularly if you've got lots of outputs, you can use that power calculation utility. And that's available either as a separate download, or what you can do is you can use PAC Machine Edition, and it's part of our PAC Machine Edition programming suite. Now for the full list of modules, see the catalogue. We've got a large range of modules. We've got some with smaller I/O counts, some larger. We've got those high density modules. We've got high speed counters and so on. But in a basic system, you're probably looking at only 3 or 4 module types, depending on how many different I/O types you've got. So your final bill of materials is very straightforward. And another thing to note there is when you purchase the I/O modules, the I/O module part number is typically all you need. That includes the connection to the backplane, includes the DIN rail mounting, it includes the terminals, and the only extras you might want to add on is if you want like wire markers and other terminal options. But for many of these applications, one part number, one I/O module, that's all you need. So that means that you've got a lot of complex decisions into which I/O modules to use, but your final bill of materials for the user is very straightforward. Now, if you've got a distributed system, you can use a CPE200. An RSTi-EP I/O can be distributed using PROFINET. So we've got an I/O section later, so I'll show you how that works. It's actually very similar to what we've seen. You just use a network adapter instead of the CPU. But again, we'll come on to that when we talk about remote I/O. So let's look at a chassis-based PACSystems RSTi application. Now, as this one is chassis-based, I normally start with the chassis. Actually, you might do the I/O module calculation first and then work out how many module slots you need. But I normally start by the chassis at first, and then you can always come back and modify the chassis calculation as required. So we've got 3 different chassis options. There's a 7 slot with no local expansion, ideal for small compact applications. Maybe you've got mostly distributed I/O and you don't need many I/O modules in the CPU rack, so that's where the CHS007 would come in. Now the part numbers are slightly different this time. With the previous RSTi-EP, its EP is the prefix for the I/O modules and EPX is the prefix for the CPUs. But with the PACSystems RSTi, we've got a few more I/O module choices and also the way the different connections work and so on. So in this case, we have our older traditional part number standard, and then we start with IC, which means industrial controller, and then 695, that refers to RSTi modules which use the PCI slot. And then you have 3 letters which indicates the type of module it is. So CHS is chassis or rack, MDL would be module, CPE would be CPU with Ethernet, and so on. So we've got the CHS007, not expandable, but ideal for small applications where you don't need many modules in the CPU chassis. If you're not sure, I would normally recommend the 12 slot, which is expandable. And the reason for using the 12 slot is it gives you more module slots, of course, but also it's not too wide. This will fit in like an 800mm cabinet. Whereas if you go up to the next one, the 16 slot, this is quite a bit wider, so you might find you've got restrictions on the amount of panel space. But the 16 slot is very good for high density applications, particularly for remote I/O, but otherwise it's rarely used. Normally people use the 12 slot, and then there is a rack filler, so if you've got an empty slot you can always fill that if you need to. So again, the bill of materials is quite straightforward. It's a single part number, IC695 CHS007 for 7 slot, and IC695 CHS012 for a 12 slot. Now the next thing we add is a power supply. This normally goes in the left-hand slot. It doesn't have to, but because our older generation CPUs had a power supply in the left-hand slot, this is normally where we mount it. So you can see we've added a power supply. Typically this would be an IC695 PSD, so PS power supply, D for DC, and 040 is the standard 40 watt power supply. So PSD, it's a DC supply that needs 24 volt DC, and this has a single slot, and this is the one I would normally use. We do have a PSA 040, and that's an AC power supply using 120 or 240 volt AC. That one needs 2 slots and it uses an AC voltage. So this is rarely used because we normally want to keep AC power outside of the control cabinet. We want to stick to 24 volt DC. And of course, as a 2-slot power supply, you're losing a slot, so you can have fewer other modules. So I normally avoid the AC power supply here. I would rather have an external bulk mains power supply that gives me my 24 volts, and then everything that comes into the CPU is quite safe. Now, if you need more than 40 watts, then we have the PSD or PSA 140. The one means that it's a multi-purpose power supply, and then you can have 2 or more of them for either N+1 redundancy or if you need more than 40 watts. And recently we also introduced the PSD 180, which gives you up to 80 watts on the backplane. So that's a higher capacity power supply, but these are still all 1 slot. So yeah, for redundant applications, if you need redundant power supply or if you need more than 40 watts, you've got these options here. Now, if you're not sure how to do the power supply calculation, for this one, you can either start entering the configuration into Pack Machine Edition, and there's a little bar graph and a report that shows you how much current is used, or you can do the calculations manually based on the details of what's in the system manual. But anyway, the bill of materials is quite straightforward. We've added 1 extra part number. So typically for a simple bill of materials, it would be IC695 PSD040. And again, that's all you need. It's 1 part number that gives you all the power supply options. Then we add a CPU. We've got the IC695 CPE. So E means it's got built-in Ethernet. And there's a 302 and a 305, which are the basic CPUs for entry-level applications. And the difference between them is the amount of memory they've got. So the CPE 302 has 2 megabytes of RAM, which is adequate for many applications. If you've got a slightly larger application or a lot of PROFINET devices, then you might need a bit more memory. So we've got the CPE 305, which actually now has 6 megabytes of RAM. and that's a single slot CPU, ideal for entry-level applications. If you're modernising a legacy CPU, then you might use the CPE 310. This has 2 slots and it has more memory and it has 2 embedded serial slots, but it's rarely used. Normally, if you wanted serial, it's cheaper to use a single slot module with a communications module than it is to use the CPE 310. So the main purpose of a CPE 310 is if you need more than that 6 megabytes of memory. It's actually got 13 megabytes because we refreshed this recently, but it also supports a simple replacement for a legacy a CPU 310 or a CPU 315. And then we've got our flagship CPU. This is the CPE 330. This one is a 2-slot module. It's got 64 megabytes of RAM now, so much more than the other ones. It's got a built-in PROFINET controller with a built-in switch supporting MRP. And this is the one you would use for high-end and also for redundant applications. Now with this one, you don't have any serial ports. And the other thing that you have with the CPE 330, you've got a choice of the CPE 330 by itself, or you can buy a CPK 330, which includes the energy pack. So if you're not sure, I would quote the CPK 330. In the case of the CPE 302, 305 and 310, they include that energy pack. So that's an optional module that bolts onto the side of the power supply. But with the CPE 330, you do have to choose. So again, simple part number. There's no extra parts, apart from that CPE, CPK choice for the CPE 330. You're not worrying about memory cards or anything. It's just that module, and then that's the single part number, and that's all you need. Now, if you've got a larger application and you need more I/O, then you can use remote I/O via a PROFINET controller. Or if you've got a CPE 330, that's already got a built-in PROFINET controller. So that's fine for smaller or slower applications. But for high-speed applications or lots of I/O, you might want to add a PNC 001. Now, there is a slight complication here, and I don't plan to cover it in this deck, but you can have local I/O expansion using that expansion slot on the end of the CHS012 or the CHS016. So this involves adding a local rack expansion, and then we have a range of IC694 expansion I/O modules, but that's a bit more complicated and a bit restricting on some of the I/O you can have. So I prefer to use PROFINET for expansion, but if you do need to optimize your bill of materials later, or you have a larger system, then yes, certainly that local expansion I/O, that can help you reduce the price compared to using PROFINET I/O with PROFINET controllers and PROFINET scanners. So for the CPE 302, 305 and 310, or for larger and high-speed applications, again, you add a PROFINET controller. So that's part number IC695PNC001. Again, nice simple part number. If you've got a CPE 330 for standard applications, you've already got a built-in PROFINET controller, so you don't need any extra hardware. Now that IC695PNC001, that has 2 built-in copper ports supporting the media redundancy protocol, so you don't need any external switches or devices. Same with the CPE 330, that PROFINET controller has a built-in switch. With the PNC001, you do actually have a 4-port switch there, so there are 2 extra ports you can use, and they are small form factor ports. So potentially you could consider adding an SFP to the PNC001 to give you additional connections. But that's, again, quite an advanced aspect, which I won't really cover much in this deck. So what you can see here is very simple. If you need remote I/O, on the CPE 302 application, we've added a PNC001. And on the CPK 330, I haven't added anything because we've already got PROFINET built into the CPU. So, like the CPE 200, if it's local I/O, then you add local I/O modules. So we've got a range of modules here, and depending on the density, generally with the 16-point modules, they are a single part number, but with the high density modules, you do need to add a terminal block. And the reason for adding a terminal block is it gives you more flexibility on the terminations. You can either have screw or push fit type terminations. And also, depending on the I/O wires you use, particularly if you've got thicker insulation, we offer a standard terminal, or there's a deeper terminal block as well, which is going to support more wires. So standard modules here include the MDL645, and the MDL660. Note that those part numbers begin IC694, not IC695. And the reason is the IC694 modules use the legacy serial I/O backplane on the chassis rather than the newer PCI backplane. So that's why they're indicated with 694. It just indicates what connection type they have. But we've got the 645, which is 24 volt DC in with 16 points, and the MDL 660, which has higher density, 32 points, but you do need to add that terminal block with the 660. On the output side, you could use an MDL 742. This is a 24 volt DC output. It includes electronic circuit protection on the outputs, and this gives you 16 points. Or for higher density, you could use the MDL 758, which has 32 points. Again, pretty sure that one's got ESCP as well, but for that one you'd use this IC694TB terminal block. For the analogs, for those ones again, you've got a choice of different modules. If you were doing HART, then you would use an IC695, so that's using the PCI connector. You'd use an ALG626, that's an 8-channel supporting HART, again requiring a terminal. And on the output side, you'd use an ALG728. So again, that's an analog output, 8 channels, again with HART, and it does require a terminal block. Now, we've got a large range of modules for PACSystems RSTi-EP I, including lower and higher density, different voltages. We've got a variety of different analog inputs and analog outputs. We've got RTDs and thermocouples. We've got isolated modules. We've got analogs with HART or without. Again, isolation, there's a lot of different options there. So consult the catalogue for a full list and also to determine what terminals you require. If you've got empty slots, you can then add an IC694 ACC310 filler module. And again, there are the possibility of using expansion racks, but I didn't want to cover that too much in this slide deck because it adds too much complexity. But the system manual gives a good explanation of how to use expansion racks. So the final bill of materials here is pretty straightforward. You've got your chassis, you've got your power supply and your CPU. In this case, we've got 4 I/O modules along with the standard terminal block, which is the IC694TBB032. So this gives you screw terminals with medium density. And because I've got a spare slot left at the end of the chassis, I've added 1 filler module. So relatively straightforward bill of materials. There's not too much extra in the way of terminals. There's no extra memory cards. You haven't got to worry about lots of different termination and chassis options. The power supply is quite straightforward. So a nice simple bill of materials to meet the requirements of your application. Let's move on to the PACSystems Edge Controller. So straightforward, we add the Edge Controller CPU itself. It's a self-contained CPU, so there's no separate chassis, power supply, communication modules and so on. It's a single device. So you've got the CPE400, which is our Edge Controller with 64 megabytes of RAM. And this has got built-in PROFINET, and it will support 32 I/O devices in simplex mode or 20 I/O devices when you use it in hot standby redundancy mode. But again, a nice single part number. But you have got the addition of do you want the energy pack or not. So the CPE400 is without the energy pack, and then we've got the CPK400, which includes the energy pack. So again, choice of part numbers with or without energy pack. I would normally quote with the energy pack, but not every application needs that. You've then got the IC695 CPL410, which gives you 64 megabytes of RAM as before. Now we've got the same Edge controller, but the L stands for loaded. So this one includes Web HMI, and it also, with the 410 designation, that indicates it's got an increased number of I/O devices. So this one will support 64 I/O devices in simplex mode and 32 I/O devices in hot standby redundant mode. So again, choice of part numbers for with or without energy pack. CPL410 is without, and CKL410 is with. And we moved the K, so sometimes the part number convention falls apart a bit. We didn't want CPK because we've already got CPK for the 400, and we want to keep the L for the loaded. So in this case, we've gone for CKL410 as the part number. But again, nice and simple, a set of simple part numbers, and that one part number includes everything you need. You don't need to worry about any extra devices or memory cards or anything else. So single part number gives you what you want. Now, the great thing about the Edge controller is it's got built-in redundancy support. So if you need redundancy, simple, just double up your quantity of CPUs. And what you do is you use LAN port 3, which has a dual Ethernet port. You connect both those ports together via Ethernet and you have your synchronization. Combine that with the built-in PROFINET controller using LAN 2 ports, which includes MRP capability, and now you've got a hot standby controller system with a fault-tolerant I/O network. So very simple to build up redundancy using 2 CPUs rather than 1. Effectively, you're getting redundancy for the cost of a spare module. Now, the Edge controller doesn't have any local I/O. You have to use PROFINET, or you could use Modbus TCP, I guess, or you could use some other protocol with a gateway, but effectively, whatever you do, it's remote I/O. So you can use PACSystems RSTi remote I/O. I would normally today use PACSystems RSTi-EP remote I/O, which gives you a more compact I/O solution at a lower price. That's our preferred solution. So we'll cover these later. And also available, because the Edge controller supports -40 to +70 degrees C, if you needed I/O that also supports -40 to +70, then that's where the PAC 8000 remote I/O might come in. Anyway, we will be covering I/O in a later section. So if you wanted redundancy or high availability with the Edge controller, it was simple. Just add an extra Edge controller and then it's a couple of Ethernet cables to wire them up. With PACSystems RSTi, we use a slightly different arrangement because instead of using Ethernet for synchronization, we use reflective memory. So that means we need to add the reflective memory modules. So let's cover how that works. So a bit like the Edge controller, we do have some duplication. There's 2 of everything, and then we've got those additional RMX modules. So we start with the chassis. Now I would say that for most redundant applications, the CPU chassis isn't going to contain that many modules. It probably isn't going to have any local I/O because then you'd have duplicated I/O, and we normally have I/O on PROFINET. So that means that really all you need is the power supply, CPU, the RMX modules, and maybe PROFINET modules, maybe serial modules, but even adding all those together, you probably only need a 7-slot chassis. So I would say that for most applications, you'd have quantity 2 off IC695 CHS007. We then add the power supplies. So again, for most applications, single slot 24 volt DC, so the IC695 PSD040 would work. Now I have seen some applications where people specify redundant power supplies on the CPUs, but we've already got redundant CPUs, so I don't see how adding redundant power supplies really helps. So provided those independent power supplies are provided from different voltage rails, you then eliminate any single point of failure. But if people are really into redundancy, you could add a PSD140 into each chassis and you'd have 2 of those, which would have total quantity 4. But I would say for most applications, there's a law of diminishing returns, and adding redundancy on top of redundancy doesn't really help you much. And actually it can either make the system less reliable, because the more components you add, of course, the more likelihood there is of a single point failure. However, you could argue that reliability isn't the same as availability, but that could be a very long and detailed discussion. So I would say for most applications, you've got redundancy at the CPU level, so you only need 1 power supply in each chassis. So 2 CHS007, 2 PSD040, nice and simple. Then you add your CPUs. In this case, there's only one choice because only the CPE 330 supports redundancy, so you'd add the CPE 330, and then your only decision there is, do you want the energy pack or not? And in a budget quote, I would normally add the energy pack just to be on the safe side. It could always be removed later, but that would normally be an engineering discussion. So again, nice and simple bill of materials with 2 chassis, 2 power supply, 2 CPUs. Again, remember those CPUs have got built-in PROFINET, and that's with a switch using MRP. So at this stage, you might have all you need in terms of communications. We only need to add the RMX modules. A PROFINET controller might be needed if you've got a high performance application. So the criteria here is how many devices have you got, and how fast performance do you need. So if you've got less than or equal to 20 I/O devices, then use the built-in PROFINET controller. And provided your response time is at 16 milliseconds or above, then again, use the built-in PROFINET controller. If you've got more I/O devices, this is where the PROFINET controller PNC001 comes in. With this one, we can support up to 62 I/O devices per PROFINET controller. And if you needed more than that, potentially you could have additional PROFINET controllers. But also from a performance point of view, the PNC001 will support 8 devices at 1 millisecond each. So if you've got very high speed updates, then that's where you might want to use the PNC001. You could also add it in now just to be on the safe side. And of course, you could always remove that later if you want to optimize your bill of materials when you understand more about the application. The other reason for having a PNC001 is it also frees up the 2 Ethernet ports on the main CPU. So yeah, maybe you're adding a PROFINET controller, not because you need the performance, but just to make sure you've got plenty of Ethernet ports. Alternatively, you could also add an Ethernet module IC695 ETM001. That would be another way of doing it. So multiple options here, but this one I would say is the most straightforward. CPU, power supply, chassis, and then add a PROFINET controller, particularly for larger applications. As I say, for small applications, you probably don't need this PROFINET controller. And then we need the actual synchronization modules. So the synchronization modules are based on reflective memory, and they have part number IC695 RMX. So we've got our standard RMX128. This is a single slot module that has multi-mode fiber. Multi-mode fiber will support distances of up to 300 meters between your controllers using a pair of multi-mode fibers. This is the one I would normally recommend if you're not sure what the user needs, but we do have the option of the RMX228, which uses single mode fiber, and this can give you considerably longer distances. But 300 meters is already quite a big distance. 300 meters allows you to have the controllers in separate cabinets or even in separate rooms, or possibly even in separate buildings. But where you might go to single mode is if you want a much higher distribution between the CPUs. For example, if you've got a bridge or a tunnel, single mode fiber would allow you to have one controller at one end of the tunnel or bridge and the other controller at the other end. So thinking about disaster recovery, even if a truck or lorry drove off the highway, wiped out a complete building and took out all of the controller with it, by having a separate building at the other end of the tunnel, this could give you very good disaster recovery responses. But most people don't go that far. They're just worried about the controller failures. And the worst that might happen is someone tips a cup of Coke or coffee over the controller, in which case 300 meters with redundancy in side-by-side panels is probably more than enough. Now there is a question about how many RMX modules you install. For many applications, 2 would probably be enough. So you have 1 RMX module per chassis, but we do recommend 4, that's 2 per chassis, for the best failure mode coverage. The reason we recommend 4 is there is a failure mode where potentially if a single RMX module failed and you only had 1 in the chassis, that would mean the CPUs wouldn't be synchronized. Under normal circumstances, that wouldn't be a problem because the application relationship of the PROFINET I/O would mean that they only work with the primary or master controller. But there is another failure mode where you get subsequent failures. Potentially if you had an RMX or a synchronization link failure and then you had a subsequent PROFINET failure, it could be that you get some I/O being controlled by one controller and other I/O being controlled by another controller. Now that may or may not be an issue for your application. So this is why we recommend 4 for best failure mode coverage, because the likelihood of 2 RMX failures or 2 redundancy link failures is a lot less likely than 1 link failure. Of course, again, you've got to be careful there because if you've got your fiber cables and you're running them side by side along the same set of trunking, then you could potentially have a single mode failure. So this is where failure mode effect analysis might come in to determine what are the possible causes of failures, what are the possible implications of failures, and that's where you might decide about how many RMX modules you go. But then you're also into that question about redundant power supplies, you're into the question about cable routing, and then there's a whole load of other questions there. So for a typical application, If it's a budget quote, I would quote 4. You've always got the option of going down to 2 later if you need it. And then in this instance, because we have a PROFINET controller, we've got the 2 RMX modules, that uses up 6 slots in the chassis. We've got an empty slot, so I would fill that with a filler module. And then we've got 2 of everything, apart from the RMX, of course, where we've got 4. So again, nice, simple part numbers. We've got the chassis, the power supply, the CPU, the PROFINET controller, the RMX modules, and a filler module in each chassis, and then multiplied by 2 for redundancy. Now, optionally, you could add our fibre optic cables. We only do these in quite small lengths though, but the idea is here to synchronise the RMX 128 modules using multimode fibre. Because we expect many users to have quite a short distance between the controllers, we do provide those shorter cables. So the part number is IC695CBL010. FD is full duplex, SD is simplex. The difference is that with full duplex you get 2 cables, with simplex you just get 1 cable, so you'd need to use 2 of them. Why would you buy 2 simplex cables? Well, one of the obvious answers there is if you've got separate cable routes, but I would say that because you need both cables in a redundancy link, I would say you're normally going to use the duplex cable. I don't see any point in the simplex cables, but there may be applications, so that's why we offer simplex as well. So we've got a variety of different lengths. XXX is the length, and we typically offer like 2 is a 10-foot or 3-meter cable. I think 5 is a 5-meter or 15-foot cable. And there are other lengths, but they're not very long. So they would be fine if you've got 2 cabinets side by side, or maybe your redundancy controllers are in a single cabinet. Again, think of that failure mode effect analysis. If you've got a single cabinet and someone spills their coffee or Coke in the cabinet, they could take out both CPUs at the same time. So you do need to think of these single mode failures. But anyway, I'm getting a bit beyond myself here. So again, for longer distances, we can provide slightly longer cables, but I would often expect that most users would make their own cables. Particularly if you go longer than our standard, which I think is 5 meters, 15 foot, any longer than that, and you're probably looking at making your own cable. And if you're using RMX 228 modules for single mode, then we don't provide single mode cable. Again, your user or you as an integrator would buy and make those cables. But again, the part number bill of materials is still quite straightforward. We've just added on that extra cable numbers. So for duplex, we've got 4 RMX modules. You need 1 duplex cable per pair, so that means 2 cables. Now, it is possible to have local I/O with a redundant system, and the reason you might want to do that is if the I/O is redundant itself. But for most applications, people are concerned with CPU redundancy, but they would have simplex I/O as long as the I/O network itself is fault tolerant, and that's where PROFINET comes in with media redundancy protocol. So for the I/O, typically for a redundant system, it's remote I/O, and we can do that with PACSystems RSTi or PACSystems RSTi-EP, or possibly PAC 8000 I/O, but we'll look at these in the separate remote I/O section later. And here we are at the remote I/O section. So we've configured the CPU. Sometimes the CPU will have local I/O, in which case we don't need any more I/O. But if you are having remote I/O, then these are the basic options. So we'll start with the PACSystems RSTi-EP I/O, and this is intended to be low cost slice I/O that takes up minimal panel space, but still gives you some very good I/O capabilities. So the configuration process is similar to the CP200 range, except instead of having a CPU, we now start with a PROFINET scanner or a network adapter. So assuming it's PROFINET, which is our preferred protocol for I/O, then you can either have the EPX, so that's a standalone device, PNS is the PROFINET scanner, 001, that's for simplex applications, and if you've got redundant controllers, then we use EPX PNS 101. So again, single part number, that includes the DIN rail endpoints, it includes the DIN rail mounting, the power supply connections, the terminals, so 1 part number is all you need. Then we add the I/O modules, and these are the same as for the CPU. So no difference, same I/O modules, same range, same about the 1-wire, 2-wire arrangement, same with the output power feed modules. So again, see the full catalogue for all the I/O modules, and also for the power calculation utility, that can tell you how many power feed modules you need. So again, nice simple bill of materials with a minimal set of part numbers. You don't need to worry too much about any extra terminations and so on, because they're all included. Let's look at PACSystems RSTi PROFINET I/O. Again, similar to a PACSystems RSTi CPU system, but now we have PROFINET scanner rather than the CPU and controller. So we start with the chassis. I would say the 7 slot is very rarely used for I/O. The only time I've seen the 7 slot used is possibly where you're upgrading legacy Genius I/O blocks and you need the combination of inputs and outputs and diagnostics. Otherwise, for Genius I/O, we do have the IC695CEP 001, which gives you a single slot with an embedded PROFINET controller. But for larger applications, we normally start with the CHS 012, which is a 12 slot. This is the most popular. And then we do have a 16 slot as well, but that's quite a bit wider, so you'd need to take care of will it fit in your panel space. But either way, you end up with a single part number, and that's your chassis. Then we add a power supply. Again, for most applications, it will be a single slot PSD 040, which is 24 volt power supply. If you wanted redundant power for the I/O, you could consider using 2 PSD 140s. I've seen that quite a few times where people want redundant power to the I/O because the I/O is often simplex and the power supply is considered as the weakest link. So you could have 2 PSD 140s, they're your multi-purpose power supplies, and they support N+1 redundancy, and they're suitable for use if you need more power or if you need redundancy or both. And these days we've also got the PSD 180. The AC power supply, very rarely used, but again, yeah, quite straightforward. You end up with 2 part numbers now for your chassis and power supply. Now, because this is remote I/O, we don't need a CPU. Instead, we use a PROFINET scanner. So for most applications, including redundancy, you would use the IC695 PNS001. We do have the advanced PROFINET scanner, which is IC695 PNS101. So this is only used if you need sequence event reporting or sequence of event recording, and that has extra firmware to allow us to record inputs at 1 millisecond intervals from specific I/O modules. But for most applications, including redundancy support, you would just use a PNS001. Now that PNS001, it's got a built-in 2-port switch with copper ports, but again it has got optional SFP ports, so you could add SFPs if you want to use that as a 3 or 4 port switch, but for most applications all you need is just a PROFINET scanner. So again, nice and simple, single part numbers. And then you add your I/O modules. Same as before, same range of I/O. IC694 and IC695 modules will all work with a PROFINET scanner. So again, see the catalogue for the full list. Same range of terminations. We also get HART pass-through through PROFINET, and you've got that same filler module to fill empty slots. So again, very straightforward. And it's also a bit simpler this time because you haven't got that local expansion option. So that PROFINET scanner, it's one chassis, and if you need more than one chassis for your I/O, then you would have another chassis with another PROFINET scanner, and each one would be an independent I/O drop. So again, very straightforward to build up your bill of materials using the required I/O modules, and the only difference between this and the CPU is PROFINET scanner, and of course at this level there's no redundancy, so that's pretty much it. So let's move on to programming software choices and any extras that you might need to add onto the system. We'll then follow up with some examples. So if you're a system integrator or OEM, you may already be taking advantage of our SP OEM packages that include programming software, but for end users, as an option, you can quote the programming configuration software, which is PAC Machine Edition. So to cover the full range, we have PAC Machine Edition Professional, which is ME and then the XX is the number. So these days that would be version 10. So ME100 for version 10, and then MBP001, that's Pack Machine Edition Professional. If you've got a micro PLC or a CPE 200, we also have a light version, which is MBL001. And there is another part number. There's also MPP, which is the Pro Plus version, and that's used if you want to integrate our safety system or if you want to use MTP. But for the majority of applications, MBP covers the full range, including the edge controller, and then for CPE 200 only in micro, it's MBL. So you could add that on as an extra line. Note that the programming configuration software does need to be quoted through our Salesforce quotation tool. This can't be quoted easily as a part number, so normally you would involve customer care. And the other reason for involving customer care is that this includes a primary support package. So based on the software that the customer uses, we have this optional primary support, which is the service contract to cover both technical support and upgrades for the software, but it also covers the support for the hardware as well. Here are some more optional extras you can consider. One option is a list of spare modules to go alongside the installed modules that you will have. So that's one of every module, and the way I like to quote this is for every 1 to 10 modules, I quote one spare. For the next 11 to 20 modules, that would be a second spare, going up to a maximum of 4 spares, and then that way you've got enough spares for the user that if they do have any problems with the installed equipment, then they can install that spare on the basis that of course they'll replace that spare if it is used. Another option is also to have those spares as a spare system which can be installed in their lab or their maintenance depot, so they can have a live system to test on before they deploy to site. And also you could potentially even look at other uses of those spares. For example, with the edge controller, if you've got a simplex system, you could install the spare and then you have a redundancy system and your spare is live, and now you have hot standby for the cost of your spare. So there's lots of options with spares. Other options would be to add operator interfaces, for example, a Quick Panel Plus, or maybe an industrial PC or panel PC with Movicon software. We can also supply variable frequency drives, servo motion. Maybe you could add safety control and I/O. So certainly there's the RSTi-EP safe feed input modules there. For networking, we have switches. There are also power supplies, and then there are services. For example, I mentioned the primary support. So primary support is the option for the Pack Machine Edition software that can give the end user both the Pack Machine Edition software updates, but also enables them to access our technical support line for all of the technical support on the hardware. So lots of optional extras that can be added in as required. And I would normally mention these as options, and then we can either quote on the basis of as requested, or you could even give these line by line items as part of your primary quotation. So these are the current operator interface options. The Quick Panel Plus, which soon will be replaced with the PACSystems operator interface. But you've got a 6-inch unit. The 6-inch unit is rarely used because it's a small display and it's a touch screen using resistive technology. But then you've got the 7-inch, which I think is a good unit because it's the lowest cost, but it gives you a very good TFT touchscreen with multi-touch capability using capacitive touch. The 10-inch is like a sweet spot, so it's quite a bit bigger than the 7-inch, but it's not as expensive as the 12-inch. So that's good for sort of medium applications. And then you've got the 12-inch, which is the same resolution as the 10-inch, but a physically bigger screen. And then you've got the full-size 15-inch. And next year, with the operator interface from the PACSystems range, we'll have all of these sizes, but we're also planning 19 and 24-inch, and those will move to widescreen models. So they'll be more modern and up-to-date, with higher resolution, an updated operating system, and just more modern and better performance all round. Another option, of course, is the RXi display, which is a panel PC, and you could use that with Movicon software. Either the full Movicon Next, which is our HMI SCADA software for Windows, or maybe Web HMI if you wanted to keep the price down, but that uses a web-based interface, so the graphics performance isn't quite as good, but it does have some cost benefits. For network switches, we've got a range of unmanaged switches. There's a simple 5-port and 8-port switch. There's a 24-port, and there's also a 4-2 port switch. So the idea of the 4-2 port is it's got a combination of copper ports, and then there are 2 either multimedia or a single mode type fiber ports as well. So that allows you to have like a backbone arrangement on fiber and then copper ports down to your devices. So those are unmanaged switches, ideal for use at the higher level between the PLC and HMI SCADA. For people that want managed switches, we've got a range of managed switches as well. So again, starting with an 8-port managed switch, and then again we've got like those 4-2 or 8-2 or 16-2 or an 8-4 port switch, which combines copper with multi-mode or single mode fiber. And there are some additional switches in that range as well. The benefit of a managed switch is that it gives you more network capabilities in terms of being able to set up things like VLANs and being able to control what the network does and being able to monitor the network. And then for PROFINET networks at the IO level, we've got switches in the GLM range. So again, there's 6, 8 or 10 copper ports with a choice of 4-2 or 4 again. These would be SFP ports. So you could buy optional SFP again to give you that nice fiber backbone with then a standard copper network. And the benefit of using a PROFINET switch is that it supports media redundancy protocol and it supports a GSDML file, which means that you've got the full support for the PROFINET interface and diagnostics into the PLC. And here's the range of power supplies. We've got our essential or value SVL. So these are mains to 24 volt Ds in the range of 4, 10 and 20 amps. We've got the advanced SDNC range. So they're available with or without conformal coating. And again, mains to 24 volt DC. And these are available as 5, 10, 20, 40 amps. There's also 3-phase versions in the 10 and 20 amp version as well. The benefit of the advanced ones is that they have better power regulation and they also include ATEX approval. So if you have a more rugged environment or you need ATEX, then that's where the advanced power supplies come in. Otherwise, you can use the essential and value series. And then for redundancy applications, we also have redundancy modules as well. So you can have 2 power supplies with a redundancy module, and that gives you power supply redundancy. So if one power supply was to fail, the other one would take over, and the redundancy module isolates the failed power supply to make sure there's no interaction on the power supply output. So that's what you use typically for I/O. You would use a redundancy module along with 2 power supplies to give you your I/O supply. For redundant PLCs, I wouldn't use a redundancy module. I would just use a separate power supply for each CPU and do it that way. So that saves you a bit of cost and it also simplifies the wiring. So, and of course, yeah, that also fits in with the redundancy scheme. So again, another option that you can add, again, there's an option. Yeah, some people aren't buying power supplies, they're just buying PLC components. But if they are buying power supplies or if they realise there's an option to get them from a single vendor, then we can simplify their purchasing arrangements. And also it can result in a larger order, which can mean that they could get potentially a bigger discount. And also from a technical support point of view, getting all of your support from a single vendor can make life easier as well. So let's take a look at some sample bill of materials. I'm going to take some random I/O counts. Typically in a system we see that the number of discrete inputs is the largest, followed by the number of discrete outputs, followed by the number of analog inputs, followed by the number of analog outputs. That's certainly true for discrete and hybrid applications. It may be that for applications which have a lot of process control there are more analogs, but the process is the same. You take the number of I/O of each type, relate that into the particular module type you want to use. So for example, if you have a 24 volt DC in, you might use the EP125F. So you look at the capabilities of the EP125F, which is 16. So you divide your I/O count by 16 to work out the number of modules. And of course, if there's not an exact number, you would round up. And also, as mentioned before, you could add the spares count as well. So quite simple to calculate the I/O modules. And then based on the number of I/O, you can use that to calculate the CPU, how complex is the application. And then there's all those other factors like, do you need redundancy? Is it remote I/O and so on. So here's our first requirement. So this is for a smallish system. It's between about 100 and 150 I/O. And by the time you've added spares, there might even be a bit more. But in this case, I'm assuming that the I/O count includes the spares requirement. So we've got 64 24 volt DC in, 48 24 volt DC out, 16 analog in, and 6 analog out. And I see a lot of sort of systems around about this size, particularly for things like skid control and remote I/O and other applications. It's a reasonable enough size, not too complicated, not too big. And for this, because the I/O count isn't too large, potentially in future you could do this with the PACSystems Micro PLC. Today, of course, we would do this with the compact CPE 200. So my bill of materials is over here on the right. I have one EPX CPE 210. Probably for this I/O count, I could use a CPE 205, but I've gone for the CPE 210 just to give me a bit more memory in case it's a more complex control algorithm. And that also gives me the opportunity to optimize the BoM if needed. But an EPX CPE 210 gives you a good combination of the two separate Ethernet ports with the possibility for PROFINET. It gives you the greater processing power with more memory. So it's just that bit bigger than the entry-level CPU. On the input side, 64 divided by 16 is 4, so I have 4 EP125F modules. 48 divided by 16 is 3, so I have 3 EP225F modules. Because of the amount of EP225Fs, I've quoted 2 EP7641s. So that's probably more than I need, but without knowing exactly what's required on the output side, effectively what I've got there is a 10 amp supply for the first EP225F, and then 2 more 10 amp supplies for each subsequent 225F. That's probably way more than we need, so you could do a power supply calculation, but at this level, that makes sure that I have more than enough output current for any possible output situation. Then on the analog side, I've got 16 analog in, so 16 divided by 4 means that I need 4 EP3164 modules. Again, potentially I could optimize here. I could use 2 of the 8-channel modules, but then I also need high-density terminals, and it just gets a bit more complicated. So for simplification of the bill of materials, I'm using the EP3164. And then the last one there, I've got 6 analog outputs. 6 divided by 4 is 1.5. You can't have half an I/O module, so I've quoted 2 EP4164s. So that's a complete bill of materials for the control system to cover that I/O count there, including the power distribution based on the number of I/O times 0.5 and then divided by 10 minus 1. So that's the worst case power supply calculation. I'm not taking into account any sort of simultaneity there. It's quite likely that I don't need both of those EP7641s, or maybe even any EP7641 again at all, but you need to do a calculation on the actual output. So to avoid any issues at this stage, without knowing what the outputs are, I've just quoted for the maximum current possible. Otherwise, that's all the components I need. So a very straightforward bill of materials for this compact size application. Now here I've got a slightly larger system, so not much larger than before. It probably doesn't deserve using the CPE 200, except there's a requirement to use HART I/O. So for HART, then the only good HART solution we have, including HART pass-through, is using RSTi I/O. If it was just analog inputs with HART only and we didn't need pass-through, there is now an RSTi-EP HART module, but it doesn't include the full HART pass-through, it just has some HART capability. Another possibility might be to use external HART multiplexers, but again, what I want to do is provide Emerson components without too much third-party complexity. So using the RSTi HART modules, we can conform with the requirements and use local I/O, and we have this nice solution here. So I've got 96 discrete in, 64 discrete out, 16 HART inputs, and 6 HART outputs. So as before, we need the CPU. So because it's an RSTi, I choose my CPU. That also needs a chassis and a power supply. I then take my modules and I divide them by, in this case for the discretes, it's 32. So I can use a 32 channel module. So I'm using 3 MDL660s, 2 MDL758. I've got 1 ALG626, which is the analog in 16 channel with HART. 1 ALG728, because that's got 8 channels and I only need 6, so that leaves me with 2 spares. And then if you count up the modules, I've got 1, 2, 3, 4, 5, 6, 7. So I need 7 terminal blocks. And then that leaves me with 3 empty slots. So I've added in the optional filler module. So again, this is a comprehensive solution for a PLC with HART I/O and including the capability for HART pass-through up into Emerson's AMS or to some third-party device type management software. So here's the bill of materials for a redundant solution. So again, similar I/O count to previously, but because HART isn't mentioned, I'm going to stick with RSTi-EP I/O to keep the price down. And for redundancy, I'm going to use the edge controller, again, to keep the price down. So the benefit of using the edge controller, it's significantly cheaper than an RX3i with RMX, possibly to the extent that it's about half the price. Because you don't need all of the RMX modules. It's also significantly more compact. With the RX3i you need more panel space. The edge controller uses significantly less panel space. So because HART isn't mentioned, I'm going to use RSTi-EP I/O. So again, we take the number of modules, 96 divided by 16 is 6, 64 for the outputs divided by 16 is 4. I've added in the power feed modules again, so effectively here I can spread the load across multiple modules. You may need slightly more EP7641, or you may be able to get away with slightly fewer, but again, without knowing more about the application, I've effectively gone for one EP7641 for every EP225F minus 1, because I've also got 10 amps from the actual CPU power supply. And then on the outputs, 24 divided by 4 is 6, and 16 outputs divided by 4 is 4. So again, a nice simple architecture, 2 CPUs which are self-contained. Notice I've gone for the CPK400, which includes the energy pack, and then I've got my single I/O drop, and that can use PROFINET with MRP for redundancy. So because it's redundant CPUs, I've had to go for the EPX PNS101, but now I have a fault-tolerant network, hot standby CPUs, and simplex I/O. So that's a very cost-effective redundancy solution that's both economical on panel space and on power, and also very simple to implement as well, but that's more on the programming side. But a nice simple bill of materials for a redundant control system for a smallish type application. So here's a larger redundant application. I've got more I/O, 192 in, 128 out. There's also a requirement for HART, and it's possible that in this case the client is also requesting high-speed bumpless failover. So with the PACSystems edge controller, the failover time is 300 milliseconds, pretty much regardless of what the scan time is. But with the PACSystems RX3i, I can go to single scan failover, and I can have very fast scan times. So a typical failover time would be in the order of between 5 and 20 milliseconds. So first of all, I need my redundant control. So I'm going for 2 CHS007 7-slot chassis, 2 power supplies, 2 CPK330, so that's the CPE330 which supports redundancy, along with the energy pack. For this one, I'm only going to use 2 RMX128s because I'm trying to keep the price down. And what we could probably do is explain to the client that, there is this issue of this dual fault tolerance issue, whereas if you get 2 failures, you might have redundantly or separately controlled I/O. But if they're willing to live with that, then we can keep the bill of materials for the CPUs quite simple. So again, no separate PROFINET controller because I don't have much remote I/O. And also maybe the application isn't that high speed on the I/O side. Remember, we can still achieve 16 milliseconds quite easily with the CPE330 built-in controller. So in this case, no extra modules required. And the only thing I've added in there is an optional duplex multi-fiber cable, just of 3 meters. So if they're going to go in the same panel, then that's all you would need there for the CPU. So the CPU calculation is quite simple. And then the I/O is remote I/O. So I do that as a separate calculation. So I take the number of modules and divide by the module count again. So MDL660, 32 channel module, 192 divided by 32 is 6. 128 divided by 32 is 4. I've got 48 modules with HART, so 48 divided by 16 gives me 3. 32 on the outputs divided by 8 gives me 4. So if you add all those modules up, that's 17. So I need 17 terminal blocks. And 17 is too many modules to fit in a single 12 or even a 16 slot chassis. So what I'm going to do with this one is I'm going to spread the remote I/O across 2 remote I/O drops. So each of those I/O drops will have a 12 slot chassis, a PROFINET scanner, a power supply, and then I've also then added up how many modules in total, and I've worked out how many filler modules I've needed to make sure that every slot is filled. Okay, so again, a nice straightforward bill of materials. We're supporting media redundancy protocol for a fault tolerant network. We've got the required number of I/O including heart. If you wanted to bring the price down, what you could consider is running the discrete I/O as RSTi-EP and the analog I/O as RX3i. So you could bring the price down that way. There's not too much savings we can do in terms of the CPU, but maybe if the customer doesn't need that one scan failover, they could move to a CPE 400 edge controller solution. Alternatively, for better control on the CPU side, you might add the additional RMX modules and add a PROFINET controller, but that would be pushing the price upwards rather than bringing it down. So there's certainly optimizations on the I/O side. We've already optimized on the CPU side. But again, quite a nice clean solution. And you can see physically here, you have 2 CPU racks, 2 I/O racks, and it's nice and straightforward in terms of the network architecture and the configuration. So a nice, straightforward, but high performance hot standby control system. Now, you could use the templates I've given you here in order to make your I/O selection. And in many cases, that would work fine for a budget quote. I've mentioned standard modules like the EP1215 and the EP225, the 225F. I've got standard modules for the RX3i, such as the MDL660 and so on. So for many applications, that would be fine. But if you need more documentation and you need to understand about some of the alternative I/O modules you've got, this is where you can find that additional information. So for basic module information, I would go and look at the data sheets. So these data sheets are on emerson.com, and you can search for the part number, or you can look at the different categories, or you could search for PACSystems or RSTi-EP I/O. And from there, you can drill down and find the data sheets. Data sheets generally give you a list of all the part numbers along with a description. And then some of the data sheets go into a bit more detail. For example, for RSTi-EP, we've got data sheets for the inputs, the outputs, the analog in and so on, which gives you more information. But if you want the full details, then you would go to our customer center and you could download the relevant user manuals. So there's a PACSystems RSTi-EP user manual that covers both the CPUs and the network adapters and the I/O modules. So the part number for that manual is GFK2958. So you would be looking for the latest version of that manual to get the latest up-to-date information. For the PACSystems RX3i I/O modules and chassis and power supplies, there's the RX3i system manual, which is a hardware-focused manual, and that's part number GFK2314. For details on what the CPUs do and how they operate, we've got GFK2222. And then if you want more detail about the energy packs, then there's an energy packs and battery manual, GFK2741. So for a point of view of the hardware configuration, those are the 4 main manuals that you would need to use, along with all the relevant data sheets. Now there is a special case for a bill of materials, which is where you're modernising a legacy Series 90 controller. Legacy Series 90 controllers include the Series 9030 that was introduced in about 1990. We sold about 500,000 of those, so there's a lot of those in the field which are still waiting to be updated. Probably as we go forward in time, more and more are getting replaced, but I still come across legacy Series 90 PLCs that have been installed as much as 30 years ago, and they're still running. So, they're still available in order to be able to maybe get some spares. Certainly on the I/O modules, you can use an IC694 I/O module to replace a legacy IC693 module. But increasingly, what you want to do is replace those older PLCs because they're getting harder and harder to maintain, and they're probably getting well into the end of the bathtub curve for reliability. So they're all beginning to fail now. So what we can do is we can modernize these legacy Series 9030 controllers very easily using the PACSystems RSTi. And also if you come across a Series 9070, the 9070 was the bigger brother of a Series 9030, and we can modernize those as well. One of the ways we do this is, first of all, we have things like support for the original I/O modules. We have similar form factors for the chassis. For 9070, we have a conversion rack to allow you to preserve the I/O wiring. And for the application, we can preserve that in many cases by running it through from the old Logic Master software into PAC Machine Edition, and that allows you to keep using the old legacy application code but updated to run in the new CPU. So for a Series 9030, we can offer a very straightforward modernization path by letting the user keep the existing I/O modules. Because they're keeping the existing I/O modules, it also allows them to preserve the I/O wiring. So this is a nice low cost, low risk upgrade. And one of the things that de-risks it is, because you've not disturbed the field wiring, if there's any issues during the upgrade, you can just put the original components back in and you're back to where you started. So of course you'll have lost a little bit of time, but it means the risk is very low and you can modernize in just a few hours. It doesn't take days or weeks, which is what it might take if you start disturbing field wiring. Instead, you're down into hours with very low risk because you've got a great fallback position. So what you need to do is look at the existing installed base. Typically there will be a CPU chassis, and the one that was most commonly installed was the IC693CHS391. So that was a 10-slot chassis with capability for a power supply, a CPU and 9 I/O slots. We replaced that with an IC695CHS012. Now, one of the great things about the CHS012 is it's effectively got the same footprint as a CHS391 and can use the same mounting holes. So you don't need to make any changes to the panel. The only thing is on the CHS012, it's about an inch or about 2 centimeters wider on the right hand side because we've got that extra expansion capability. But for many applications, provided the user followed our cooling guidelines, there will be plenty of space in their panel to easily replace the CHS391 with a CHS012. So that's your first part number, the CHS012. You then replace the CPU, and there were a whole range of legacy Series 9030 CPUs, but pretty much all of them can be replaced by an IC695 CPE302. So this is a CPU with Ethernet. The 2 megabytes of RAM you get with the CPE302 will more than cover any legacy CPU 300 range CPU application, because there you were talking about kilobytes of memory, not megabytes. And also, of course, with the CPE302, you're also adding an Ethernet port. Now, power supply, that's easily replaced by using either a PSD040 or PSA040. I recommend the PSD040 because then you're only using a single slot, and that guarantees that you've still got the full available range of slots for the older Series 9030 modules. Now, some Series 9030 modules used expansion, so that's where you can add an IC695 LRE001, but you can keep the existing expansion modules and expansion chassis. You keep all of the existing I/O modules, and even if there's an existing Genius bus controller module, you can keep that as well. So although the Genius bus controller, the BEM331, is no longer available, it will still work in the new PACSystems RSTi. And the reason it will still work is if you look at the backplane here, you'll see for each slot we've actually got 2 connectors. There's the bigger connector, which is the new IC695 PCI connector, but we've also got the older Series 9030 I693, IC694 serial bus connector. So any old I/O module will be able to be installed into the new RSTi CPU chassis. There are some modules which need attention. So for example, if you've got a CMM311 or a PCM301 or 311 module, or even an older PCM300, they can usually be replaced by an IC695 CMM002. So the reason for using a CMM311, that was normally for Modbus RTU slave. So you would need to make a new cable or a cable adapter, but the IC695 CMM002 can handle that same Modbus RTU slave protocol. The majority of PCM applications were for Modbus RTU master. So again, the CMM002 can handle that. you'd need to make a new cable or a cable adapter. You'd need to look at the logic and work out what the exchanges are and recreate those in the new system. But you can easily replace the hardware using that CMM002. The other nice thing there is that with the CMM311 and PCM301, they normally only use a single port, where the CMM002 has 2 ports. So potentially if you've got 2 or more modules, you could replace those with a single module. Now there was an Ethernet module with the Series 9030. Sometimes it was embedded in the CPU, in which case no problem, because the CPE302 has Ethernet. Some people installed an additional CMM321, and again for that one, you've either got the CPU Ethernet, in which case you don't need to use that module at all, or if you wanted a separate dedicated Ethernet module, you could add in an IC695 ETM001. Now there are some caveats. For example, if you've got an older Series 9030 PLC running C blocks, they need to be recompiled to be used on the RSTi, so you'll need the source code for those blocks. Some, but very few Series 9030 applications were programmed using sequential function chart, and that needs to be rewritten. But if it was a straightforward ladder application, then that can be modernized through PACSystems RSTi and PAC Machine Edition without any rewrites at all, other than maybe addressing these communication issues. Where it gets a bit tougher is on some maybe legacy I/O modules which aren't made by Emerson, and also if there's any sort of motion control. So if you've got any like DSM module, or if you've got an APU 301 or 302 module, those sorts of modules, then you should consult with Emerson, because the motion control will need a bit more work to update. But there's a good chance with these older PLCs, if the PLC is old, the motion control is just as old as well, and there's a good chance that motion will need modernizing. So that means replacing the motors, replacing the drives. But that's a much bigger upgrade story. So again, consult with Emerson if there's any sort of motion control other than a simple VFD interface. Alternatively, if it is using simple analog motion with high-speed counters and analog outputs, that's quite easy to replicate inside the PACSystems RSTi as well. But regardless of what it is, I recommend you consult with us so we can give you the best solution. But if you look at the bill of materials here, what you can see is it's actually very straightforward. There's 3 main part numbers. It's a new chassis, a new power supply, a new CPU, and that's all you need. And if there was any expansion, you might add in the local expansion module as well. So 3 or 4 part numbers allows you to modernize the system. And if you want to replace the I/O modules, you can do that as well, because we can replace the IC693 modules with their IC694 equivalents. So that allows you to upgrade old I/O modules as well. But often with the old I/O modules, they tend to be very low technology. It's old TTL type technology. They do last for a long, long time. So it's less likely you'll need to modernize or replace those. So it's normally concerned with the CPU. And if you have a new CPU, you also need the new power supply and chassis. But that's all you need effectively. So nice, simple upgrade just for a new rack, power supply and CPU. Keep all of the I/O, low risk, low cost, and now you've got a modern control system. Now, most modernisation efforts are going to concern the Series 9030 PLC, of which we sold about 500,000, so there's a lot out there. We also had the Series 9070, which was the bigger brother of the 9030, and it was about twice the physical size, based on VME 6U chassis. The RX7i was an update of the Series 9070 based on the PACSystems family, and that's also gone away now. We didn't sell so many of them again, but again, it was the same sort of form factor as the Series 9070 with VME, but it used 9070 I/O modules. Now, both those are discontinued. We probably sold about 50,000 9070s. Not sure how many RX7Is we sold. I don't come across many RX7Is, but there's a few. I do come across quite a few 9070s which are reaching the end of their life. So we've got a similar sort of upgrade strategy, and depending what the I/O type is, it might be that the I/O modernization is quite straightforward. A recent system I see was using field control I/O, which we can modernize with Versamax. So that was a remote I/O solution. If it's rack-based I/O, then we've got a conversion chassis and I/O module wiring harnesses, which can help keep the existing I/O wiring. So there's a variety of options here. But in many cases, It's very similar to the Series 9030 modernisation, but a bit more work for the I/O. So what we do is we would look at the bill of materials. So first of all, we'd start with the chassis and we'd replace that with an IC695 CHS012 or possibly a CHS007 if we don't need that many communication modules. We replace the CPU with an IC695 CPE302, and if it was an RX7i, then we would look in more detail to see how much memory was being used. But again, generally with the CPEs for the RX3i, yeah, they have the same or more memory than the RX7i had. On the power supply side, you replace it with a suitable AC or DC power supply. And then we'd need to pay attention to what the I/O is. So if it's local I/O, then we can use the conversion chassis along with his I/O module harnesses to keep the existing I/O wiring. And there are pretty straightforward RX3i equivalents to the old legacy 9070 I/O. It does get quite detailed in terms of the details themselves though, so I would either refer to the relevant documentation or contact Emerson and we can advise what the upgrade process is. For legacy systems using Genius I/O, that would be using the IC697 BEM731. Now we don't have a bus controller for the RX3i, but what we can use is a PROFINET controller along with the IC695 GCG001, and that allows us to keep using existing legacy or even active Genius I/O. So some modules we based on Genius I/O blocks, some used field control I/O. They're both old now, but we can still continue to control them. And then for applications using Versamax, Versamax is still active. So if it's Versamax on Genius, then you only need to change the bus controller end. Again, communication modules need attention. So CMM for Modbus RTU slave, PCM often for Modbus RTU master. Again, they can be replaced with a CMM002 as before. And then if it's Ethernet, you either use the CPU Ethernet or we add in an IC695 ETM001. So a bit more work around the I/O side. Where it can get very complicated is with VME. So one of the points about the 9070 and the RX7i, they used a VME chassis which allowed easy integration of VME modules. And at the time of the 9070 in the early days of the RX7i, there were several hundred different VME modules around. So some of those were I/O modules, some of them were motion control, some of them were communication modules. There were even embedded IPCs that could be embedded in the VME backplane. So if you come across a system with VME, if it's an I/O module, then you're probably looking at a new RX3i equivalent, but that might mean I/O rewiring because the VME modules had some strange arrangements for wiring. If it's motion, then we're into PACMotion and using PACMotion servo and drives and motors. If it's any other sort of device, then embedded IPC is probably pretty straightforward. We would move to one of our new next generation IPCs running independently, but you'd need to check what the application is. Chances are if it's an old VME module, it may be running some legacy operating system. It might be an old version of Windows, it might be VxWorks, it might be QNX, it might be, who knows, because VME is very old now. But my recommendation for VME is consult with Emerson and we can give you some guidance. But generally, the modernization strategy can be the same as the 9030. It's a new chassis, new power supply, a new CPU, and then we look at the other system components and we choose appropriate replacements on the basis of what's installed today.